and I'll check in a moment whether you can confirm. So I'll be very brief right now. You can find everything that happened yesterday on the website. I've put links to the videos that were made. I've put the presentations there, so please check it out. And for now, I'm very happy to introduce Michiel here, who's going to talk about his project, Flatland. And success, Michiel.
Thank you. I do hope that the sound works now. Let's wait for a second to see if that's really the case.
Yes, the audio
Yes.
is here now.
All right, great. So let's get started, because I think we already lost 10 minutes due to this. I'll be brief about myself. I'm Michiel Veldhuis, and I'm a teacher and researcher at the Hogeschool IPABO in Amsterdam and here at the Utrecht University. Today I'm going to talk to you about a project that we've been researching and developing for the last 5 years, and it's called Beyond Flatland in Primary Mathematics Education. And in this lecture I will briefly also touch upon some questions you asked yesterday, because there were questions about the implementation of RME, about the relationship between lower order or basic skills and higher order thinking skills or conceptual skills, and the difficulty of designing tasks, whether that with time and experience would change, and how we looked upon that. So I will touch upon these topics that were raised yesterday. The outline of my talk today is, well, first a short historical and theoretical background of this project and of the sources for this project, so the theoretical sources and some of the historical Dutch history of mathematics education. And then I will give a short overview of the teaching sequences and tasks that we developed in the domains of algebra, dynamic data modeling, and probability. I don't think I have enough time to show you everything, so I will focus on the first two, but in a PowerPoint, which will become available afterwards, you can also see what we did in the probability project. Short background about Flatland. Flatland is a famous book, like this, of the 19th century about a square that has a lot of, that experiences a lot of things, that goes into different dimensions. He lives in Flatland, but there is also the one-dimensional land of a line, and there's a three-dimensional land. His adventures are very interesting, and they inspired us to think of, well, when we look at mathematics education in the Netherlands, even though we've been working for quite some time to implement RME, isn't it still too flat? Which is related to what you maybe saw yesterday in Kees Hoogland's lecture. He showed a short historical overview of conceptual development, and he showed you where that in the 70s there was a switch from basic arithmetic towards mathematics of daily life and realistic mathematics education. I want to show you some things that in the 70s were developed and thought of to work on algebra, dynamic data modeling, and probability in primary school. These three topics I will focus on now. The group that worked on a realistic mathematics education at that time, about the development of mathematics education, was called WISCOBAS, which stands for Mathematics in Primary Education. And they had 5 goals. They want to elicit mathematizing in general, but specifically they want students to generalize, to prove, to schematize, to symbolize, and to use models, which, if you paid attention yesterday in Paul Drijver's lecture, you saw that he related with the mathematization, the horizontal and the vertical mathematization, in which these 5 goals are also coming to the fore. So these 5, let's call them skills, were related to subject areas. They were related to arithmetic, to to measurement, to geometry, probability and statistics, algebra, functions, and logic. Rogier, kan jij voor mij doorklikken? And language and logic. And to show you a short example from the history, so I'll show you something from this from 1975. They published it on a regularly basis, and this is to show you that they developed the block scheme or the block language to start with students to think about solving equations. I'll go briefly to the next, which is about constructing a time distance graph on the basis of a story of a train ride and a travel from one point to another, in which the student has to relate what happens in the graph to what happens in the story. Ja, dat is het. Then, eentje terug. Thank you. And finally, there was also the view on chance, which was a whole lesson series about how to introduce probability in primary school. They did a lot with tossing coins and thinking about theoretical probability. These three topics were used as inspiration to look now at what can we still elicit in terms of higher order thinking skills, or more mathematical reasoning skills in primary school, because we have observed that most of the Dutch textbooks and most of the Dutch mathematics education in primary school is rather flat, is still mostly focused on arithmetic and calculation procedures. That's why we started this project. I'm going to stop with this. The project of Beyond Flatland in Primary Mathematics Education. These are the three part projects, and this is the staff with whom we did this project. So there were a lot of people involved, and this is also a question about if it became a response to the question about does it become more easy with more experience? No, we spent a lot of time with all of these people to think about the task, to think about the teaching sequences, to pilot them, to try them out again, to adapt them, and to go back to the drawing board and to discuss everything again. Let me see. Okay, I'm going to very briefly say something about RME and our theoretical background. Could you? Yeah. So yesterday, Paul showed you a short introduction of RME. That's a domain-specific instruction theory on the teaching and learning of mathematics. And I will shortly relate this. He showed these principles as well. And in this new project, to try to work on these more advanced mathematical reasoning skills, we used insights from cognitive psychology, from neuroscience, and from, of course, mathematics education, didactical research, to link the principles of RME to these several theories. So the first one is embodied cognition, embodiment, which is related to the activity and the reality principle of RME. The second is representational redescription theory, which is related to the level principle, so in which you move from the concrete level to the more formal level. That was an interesting interruption. And the third is variation theory, which is very famous in the to construct sequences of tasks that we used. These three theories that we used, on the slides there are several explanations and reference to them. I'm not going to go into them now. I'm going to switch immediately to the task. So you can advance a little bit. Yeah. Okay, and then you can read that later when it's on the website. Now, yesterday, Rogier told us that one of the approaches in RME is to introduce a concept by providing context that focuses on, that elicits students to focus on reasoning and representations related to the notions that you're actually aiming at. So this is something to show you, well, that's actually what we did too. So we knew that we wanted to focus on big topics, but then we looked at what are the specific notions that we are looking for to elicit students' understanding, and then we analyzed these notions to think of tasks that would that would ask, or that would put students on the road towards developing reasoning skills in that specific domain. So I will show you what kind of tasks we developed. So that's on the next. Yeah. I'll first focus on early algebra. This was a PhD project by Mara Otte, who has submitted her thesis, and we will defend it in October. So rather soon, everything about the research results will become available at the end of October. But I'll now focus on how to teach it actually. What did we look at? So the main points were this: we focused on algebraic reasoning with linear equations, and in particular of reasoning with and about unknowns, and using algebraic strategies with that. In the context of a hanging mobile. I'll show you what it is, but it looks like that. And the embodied idea behind it was the experience of balance. And balance would stand for equality, which is of course a very important concept when you're solving equations. A short overview of the lesson series is here. So this was a lesson series of 6 lessons in which we went from the first introduction of the concept of equality and working and looking at it until actually solving equations in rather formal context, a system of equations. So we went from really informal equations until very formal equations in just 6 lessons. Okay, could you go on? Okay. And again, so this is to show you what we use. So there was a physical hanging mobile, which is a balance scale that we had a carpenter make. We used that in the first 3 lessons, and later we moved on to other contexts. So where we could see if the ideas they developed within a specific context, so the model of that context would become a model for a different context. From one equation to several equations, and there is more. Yes, relations between unknowns towards values of unknowns, which is one rather specific thing that we did differently than most people in the research literature do. You often start with very defined values, so that x equals 2, and we actually used that x had a relationship with y, or that the apples had a relationship with the number of oranges and the number of bananas. Or actually, in our context of the hanging mobile, it would be the color balls. And we went from informal to more formal notations, which is to show you how these things are related to the more. This is to show you the overall idea, and now I'm going to show you what it actually looked like. So this is a hanging mobile, and this is actually the first task we provided to the students. We asked them, what can you do to keep the hanging mobile straight? So this is actually the first hanging mobile we had, which Mara photographed in her home. I want to give you a minute to type in the chat, what can you do to these balls and to the hanging mobile without disturbing the balance? So what can you do and keep it straight? I'll give you a minute to think about that, and please type your ideas in the chat.
too wide to the left. Someone else says, you remove both sets of red balls from each side. Someone else says, double both sides or take two pink balls. Pink is probably red.
Okay.
One black is two whites. I think by removing the reds from both sides.
Okay, this is great. I'm hearing very good suggestions, and I've seen that there are many coming now, which is very good. I'm going to show you shortly what the students did. I'm going to show it like, hey, doet hij het? I'm going to show you a short video clip of how students did it. So there were two steps. They first had to think about it and then actually do it. Okay, so you obviously see that this was before the whole COVID-19 problems that we have, because they are very near to each other, they touch. Well, let's forget about that, but you can see exactly how this task would, how students could approach this task. They would first have to think about it, and when they had an idea, they could try it out, and they got, it is as if your suggestions that you just typed in the chat, as if they heard it. So they exchanged one black ball for three whites, or they exchanged one red for two whites, which is, they used the relations between the balls to think of how to keep the equality in place. In general, so without the specific relations between the balls, these are the things you can do. So these are the main algebraic strategies: restructuring, isolation, and substitution. So by restructuring, you can just take everything from one side, put it on the other side, or you can change the order of the bags on each side will not disturb the balance. In isolation, you can take away what was suggested as well. If you take the two red balls from both sides, well, then the equality remains. And you can take away different bags if you preserve the relationship between the two. So if you take one red, you should do two whites. And finally, you could, if you have different colored bags which were not displayed, you can replace them. And in this way, this was the first lesson of the lesson series, just by showing them this hanging mobile and giving them this simple question, but the time we spent on this simple question to how to formulate it and how to get them actually to get a first idea of these strategies, that took a lot of reflection and a lot of tryouts. Even though it looks rather simple, we had that took a lot of time with that big team, international team, thinking about piloting. So that's just to say, well, the development of good tasks remains difficult, no matter how much experience you get. But in the end, it worked out. In the first lesson, they actually were talking about these things. They were talking about the strategies without our telling them, this is how you should do it, this is what it's called. Just giving them the task, giving them a good question, and observing what they did. Okay, and to look at the time. Right. I'll show you a short thing from the second lesson. I'm not going to give you another exercise. I'm going to give you an exercise later on. So here we ask, can you make it clearer? And can you discover the secret rule? Let me change that. Actually, I'm going to ask you to do something in, because there were very interesting things you put in the chat. So now the question is not, can you answer this, but what do you think the students would do if you asked them this? what do students do when they get this question? So they get an image of the hanging mobile with a number of different colored balls, and the question is, can you make it clearer and discover the secret rule? Again, I'll give you 1 minute for that.
So, in the meantime, people say it's a really great idea, hands-on activity to learn about equality. I'm interested to see how you start introducing the concept of variable. Here's someone giving a solution, 3 blue is 1 black.
That's something that students, of course, would also do. They would give the solution, but we wanted them to first make it clearer.
They tell you what they did instead of how to do it? Question. Probably they will take off objects of different colors to make the comparison. They will arrange according to color and describe the relationships. I guess that they would try to discover the value of each ball. They will start to look at same color balls.
Now, these are all great suggestions and indeed things that happened. And what you're doing now, I'm not sure whether it was mentioned yesterday, but you're actually, what we're doing in short is thinking, or, well, formulating hypotheses about how would their thinking and how would their reasoning become upon encountering such a task. And that's, well, the hypothetical learning trajectory. You might have heard of that from design research, which is something that's also very near to what we're doing in realistic mathematics education. That we are always thinking about, well, what we have this task and we think this would happen. And then we actually write down, well, I think this could happen. The student could say, I don't remember the exact proportion, but 1 black is 3 blue, or they could take away balls, or they could actually take all the balls off and then say, well, this is actually the most clear. They could do many things, and then you think about that, and then you actually look in the classroom, well, what happens? And that's what we, of course, also did. So, well, let's look. Well, this is first an image, yeah. What they did, they would actually group the colors because they were mixed first. So they would group them to make the relations more prominent, better visible. And they did the same thing on paper. So they did it on the real hanging mobile and then on paper, and then they made them nicely structured. In this way, they could easily see that there were 2 reds on both sides, and then they could, little by little, isolate the unknowns and find the relation between the black balls and the blue balls. And then they would write it down of how they would have done it, which is the last. They would say, if you remove the same number until it isn't possible anymore, that's it. So the secret rule was not looking for the proportion. The secret rule was, what is actually the way you can find this relationship between these 2 colored bags. And that's something that we actually discovered after the piloting phase. Because first we always asked them for the secret rule, and we were happy with this. But then they were very much, students became very focused on finding the value or finding the relation, which would generally elicit them to actually try out different numbers. They would just say, well, if this is 1, then this can be 1, 2, 3, and then they try it in all the other equations, which is a very good, it can be a very good solution strategy. Of course, you can solve many things with that, but it is not the algebraic strategy that we were looking for, which is actually approaching from the other side to use the strategies that you can use if you're progressing through your education to more complex and different equations that are not linear equations anymore. You can very often still with trial and error. Thank you. With trial and error, you can get it a long way, but it's good if that can exist and coexists with the algebraic strategies that you can actually analyze what you're doing and focus on the relationships. All right, let's continue. I'm seeing that my time. I'm going to click myself to see what I'm going to show you. Everything will become available to you. I want to show you shortly something of the different context. So for the first 3 lessons, everything was about the hanging mobile, and in the 4th lesson we went to tug of war. Yes, with these types of questions to actually make the transfer explicit. So we have this hanging mobile, and in which of these tug of war situations the same equation is represented. And little by little the students would already be enlisted to actually use rather formal notations. Even though there is no equal sign, they use the letter to represent the different animals, and afterwards we would go to even a different context in which the tug of war is not there anymore, the hanging mobile is not there anymore, but there are just pieces of fruit that are related to each other, and they would start to use the abbreviations to reason about it, and then they would explain. Not everyone, of course, would be as clear in the explanations as this student was, but they would explain how they would have approached it, how they would use one of the equations to solve the other one, to substitute the value or the fruits by the other fruits in a way to solve the problem. Lesson 4, lesson 5, I'm going to show you just this were the type of task they got, and just to show you in the end they would get this type of task, so rather a real formal equation. I'm not going to walk you through it, but just to show you this is how they solved it. Just click, and they used all the strategies, and in the end found the answer, which was on the bottom. So they found the correct answer as well. Okay, so this was the teaching sequence of early algebra, and now I have about 10 minutes left to talk about dynamic data modeling, so I'm going to do that too. How to teach it? So we chose for time distance graphs as a specific way of working on graphical representations of change. And the context we used was moving in front of a motion sensor, so students could walk, and then there would be a graph shown on the digital blackboard. And the idea was that by their moving through space, they would link their experience of moving through space to what they would see represented in the graphical representation. The lessons went in this way, a bit parallel to the algebra teaching sequence. So first some exploration, then rather easy representations of change, so graphs from discrete to continuous, and then little by little we went on to multiple movements and graphical representations in the same graph. Okay, that is actually I showed here, from informal to more formal, and real discrete time points, and time is a continuous variable. Okay. First lesson, a question: what is motion for the students? And they would do stuff like this. They would start dancing, jumping in place in one spot. That just to activate their thinking. Next. And they got this type of task. So represent your trip from home to school, which is generally something in the summer school we also give you to do, but that's something I will now skip. But this is how students often show it. But other students actually show it with already a kind of graphical representation, or on a line. I think I have an example of that. Yeah, in this way, that they actually on one line they show, well, this, they wanted to show that they went faster here and slower there. So you have all these different types of ideas students already have of graphical representations, and then we would use those to let them think about this type of problem. So a person walks normally towards the middle and then slowly towards the end, and another person walks fast towards the middle and then stands still for 2 seconds and walks with a normal speed towards the end. I'm not going to let you think about that, but students would actually do that in front of the motion sensor. So they would walk with these instructions and then see the graphical representation over the line. In the second lesson, they went from from discrete to continuous problems, representations, and we introduced the intruder problem, which is a rich problem context in which there was an intruder in some laboratory space who stole something, and students had to solve this to find out, find out what actually was stolen from which of the laboratory rooms, and to chase the thieves in the end. So, and to do that, they got all this information with which they could do nothing because they hadn't had any instruction before about graphs, but this was to get them to actually need to find out how does a graph actually work, what do I need to know to be able to interpret what the information in the graphs to get this thief. And that's how we got them involved in our lesson series, that it was not just, well, let's move in front of a motion sensor, because only that they already found it interesting, but in addition to that, that they would actually really want to know more about the graphs as well. So this was Caroline Duizer's project. She actually defended her thesis the day before yesterday. I'll show you her thesis in a minute. Okay, next. This was the next page of the booklet on Intruder Problem. So just go on. Now this was all the information they got. And the question at first was, from which room did the burglar steal something? Okay. This was introduced in the second lesson. In the third lesson, there were more specific questions about how to interpret graphs. So we got them in front of a motion sensor, and we gave them a sheet of paper on which this graph was displayed, and they had to show, or they had to walk it, they had to recreate it on the blackboard. So I have an example of that, a short video. This is a student who has the graph in his hands and walks and tries to recreate the same graph that he sees. Okay, so what's interesting with this boy is that he actually he really looked very well at the example. So he recreated the slope of the graph that would be steeper going backwards and more slanted going forwards, and that there were only three tops. So that's why he stopped at the end. When he saw there were three tops, he stopped. So he really understood actually what it meant that was shown in the graphical representation. And so he linked it correctly to his own movements in space. Okay, let's continue. This was the setup. Let's show this video as well. This is a nice video to show you how students walked. Yeah. What they were trying to do here, they wanted to recreate letters. So they got the question, what would you like to do? I would like to make an L. So they were discussing, how can I make an L? So the discussion with the teacher was, oh, I have to walk very fast towards it and slowly back, because then I get a almost vertical line, and then I have to stand still, I get a almost horizontal line walking back. But let me show you again. There was a boy that didn't completely that interpreted the task differently. He actually showed the L with his hand. You see, so he interpreted the task as I have to get an L, and well, this is the easiest way of getting an L. Whereas the girl already was a little bit further in her understanding of the situation and knew, well, I have to walk quickly and slowly and stand still. Which was not something we expected, of course, that we thought, well, the students will think about this because we wanted them to understand that time is unidirectional, so that would they say an O, that they would find out, oh, I cannot make an O in the graph. But we didn't know that students would understand it in this way, which was very interesting, and it was a nice way of of showing that you can think through all the consequences of your tasks and all the reasoning that might come up or the action students come to do, but still you can be surprised, and it can be very worthwhile surprises that you can discuss. Let me see. All right. Furthermore, well, we focused on scaling. We showed them pictures. Well, if you want to see better what's in the picture, how do you do that? Well, then in this way, they were linked to each other. I'm not going to go into that much more. No. And then in the end, they would get graphs with more than one movement in this way. And then they were asked, well, can you describe what happens here? If this is a race or if this is something else. I think I might have some time to do the probability as well. Okay, so these were the main points of the dynamic data modeling project. Short overview of the 6 lessons. And I'm going to very briefly, I think I will use 3 minutes for the probability, so we have some time for questions, because I would like to, well, I know that there were some questions typed in the chat. How to teach early probability. That was the 3rd project we did. Generally, this is what is done. So you do experiments, you see what comes out, so you throw dice, you look at what comes out, then you try to explain the results, and then you explore the sample size, but this should be the sample space. We did it in the other way around. We started with exploring the sample space. So you get a chance generator. What are the possible results? What are all the possible results? And then think of, knowing what the possible results are, what could actually come out, and then try it out. See what happens, and then repeating to find out, does it actually correspond to my expectation. So that's where we switched, which actually also is a switch from, I showed you that in the Bisco bus time, so in the 70s, they also used the common approach. And so to show you that realistic mathematics education is not a static thing, but it is dynamic, it's still changing, still the development is still continuing, to show you that, well, with these new insights, we try to get students to reason about probability. Yeah. So there are 4 key components. Well, I already said using sample space. Then 3 guiding questions to get this sample space. So what can you get? What will you get? And what did you actually get to guide the thinking? So what can you get? Imagine that you have a coin that you toss. You can get 2 results. You can get heads or tails. And then if I throw ones, what will I get? Well, you could say I don't know. Or I could get either heads or tails. And then what did you get? Well, you did it. Then you can look back on what is it. So that this is to guide their thinking, and to guide their thinking through this scheme. So going from the theoretical probability analysis of the sample space to predicting, to finding out what actually would happen, and then looking back, well, what did happen? How does what happened relate to what I expected to happen? Yeah. And so there are the questions, they will appear. Yeah. All right. Then there's a 3rd main component, which is to think very well about the switches between, well, the predictability of particular events. So for example, with heads and tails, I know for sure that there will be heads or tails, but I don't know if I toss a coin once, whether it will be the one or the other. The switch between theoretical and empirical probability, and, well, elementary results and types of results. For instance, this is with heads. If you have 2 coins, that you can have heads, which is, well, 1 result, but that you can have heads and tails and heads, which are elementary results. There are 2, but if you look at types of results, there are, of course, 2. I'm switched up. Well, there are 2 elementary results and only 1 type of result, of which the probability to find it is different. And then we used physical chance generators for the experiments and the computer simulations. Just going to show you the 6 lessons in a short overview. Started with exploring again the basic concept, then we introduced more and more complex chance generators. So going from 1 die to 2 coins, 2 dice, to a marble scooper, which is a specific type of chance generator, and then looking back on all these things and trying to relate them to each other. Yeah. So from 1 to 4 chance generators, because there are actually 4 balls that can go into the marble scooper, and from 1 experiment to many experiments. I'm going to go and skip the tasks in here. They will become available to you. so that we have some time for questions, let me just show you again all the people involved. The names are here. If you have any questions or comments, please send me an email, or if you have anything to say. And to let you know, so Caroline Duizer, she defended, this was the cover of her thesis, she defended it 2 days ago, and the thesis will become available online rather soon. And otherwise, these are some of the publications about this project, that most of them, except the last one, are open access. So you can, if you click on the DOI, you can find them and get more information about the research results. So what did we? So I only showed you what the content of the teaching sequences and of the lessons, and I guess that you might wonder, well, what did students actually do? What were the results of what type of research did you do about this? Well, those answers will be available in those articles. Thank you very much for your attention, and I'm now ready to answer a few questions before you have to move on to the next session.
A few minutes. There's here a very interesting question. Is there a way to adapt the motion tasks to work with students if you don't have a motion sensor? Have you thought about that?
Yeah. That's a very good question. Yes, we thought about that. So about actually using the motion task without a motion sensor. It's one of the, we had several experimental conditions, and we had a condition with motion sensor and a condition without motion sensor. So in the condition with motion sensor, that was what I showed you. In a condition without the motion sensor, we did the exact same exercise, exact same tasks, but without moving in front of the sensor. And what is interesting, so this is in the thesis of Caroline, was that the results in terms of reasoning about graphs did not weren't very different in these two conditions. The condition with the physical experiences was they performed slightly better than the others, but this wasn't a statistically significant result. So this teaching sequence, so with the thinking, so with the sequence of tasks, also without the real walking, but with just an explanation of what could happen, or with images of what happened, had the same results approximately. So it's possible without a motion sensor. And it's also possible with different types of motion sensors. Many, in the literature, there are many different types that have been used. So this one was with echolocation, but there are other types in which they use small cups with holes in it, and then if you walk, you can see how far the droplets of water are spaced from each other. You can use your smartphone if you have one, and well, there are many solutions to try to find something that can detect your motion.
Okay, we have time for one more question. I think this would be most interesting to tell a little bit about the role of the teacher in those experiments. What did they do to encourage students to come up with models?
Yeah. Okay, so the role of the teacher was very important in this. Of course, in the firstly, in terms of providing or constructing the learning environment, so providing the tasks and giving the first explanations of the task, but very specifically, students would of course say a lot of things. If you, well, in the videos you saw in the Algebra projects, you saw them work with the hanging mobile, and in the dynamic data modeling projects, you saw them walking in front of the motion sensor. The teacher, well, in those two fragments, I guess the teacher was silent, but of course afterwards the students would tell what they had done and how they had approached it. So in there, the teachers were very attentive to what did the students say, does their reasoning refer to, how does that relate actually to the notions that we were aiming at, how does it relate to the algebraic strategies, how does it relate to looking at time and distance as two variables that are co-varying. So the teacher would all the time try to get students, to guide students to, well, this is the guided reinvention that you heard about yesterday, to get them step by step towards the goal of further understanding of graphs of motion and of the algebraic reasoning. I guess I have to stop. Yeah.
Yeah, I'm really sorry, Michiel. It's so interesting, but we have to stop somewhere. And that's now, because in 5 minutes, the 2 parallel sessions are going to start. Please use our website to navigate to the right session. Although, if you're going to the one about the math Olympiad tasks, then this is the place. Well, I'm very happy you're here. I'm looking forward to see you again in the other sessions, and also later today when we're going to look at the pitches once more. I hope you'll be there. Okay, bye bye. See you in a few minutes. Thank you, Michiel.